we're going through the mole concept now. So in this part, students, they conduct practical investigations to demonstrate and calculate the molar mass, so the mass of 1 mole of an element and a compound. So students conduct an investigation to determine that chemicals react in simple whole number ratios by moles. So moles is like, as we'll go through it later, it's basically a unit of measurement, a new unit of measurement. We explore the concept of a mole and relate this to Avogadro's constant to describe, calculate, and manipulate masses, chemical amounts, and numbers of particles in moles of elements and compounds. So N is equal to mass over molar mass, percentage composition calculations, an empirical formula, and then limiting reagent reactions as well. Limiting reagent reactions is something that you will always have to do no matter what chemical equation you do. So we'll go through it in a bit, but just be warned that these three are like make up the fundamentals of every single bit of chemistry that you'll study for the rest of your high school career. Okay, so let's go to the dot point. Explore the 2.2.3 now. So we explore the concept of the mole and relate this to Avogadro's constant to describe, calculate, manipulate masses, chemical amounts, and numbers. So the moles of elements and compounds in N equals mass over molar mass. Percentage composition calculations, and empirical formula, limiting reagent reactions. Cool. So what is a mole? A mole is a unit of measurement denoted by the symbol mole over here, or the symbol N. It is a unit of measurement. And what it's saying is, so if we say 1 centimeter, what makes up 1 centimeter? Well, 10 millimeters make up 1 centimeter. So the mole is used to dictate the number of particles within a specific area. So 1 mole of a substance is indicative of 6.022 times 10 to the power of 23, this number of particles of a substance. So if I say I have 1 mole of sodium, that means I have 6.022 times 10 to the power of 23 particles of sodium. So that's what the mole is. So the important thing to know here is moles don't dictate density or concentration. So if I say I have 15 moles of sodium, that doesn't mean what I have is concentrated, right? It could be very dilute because these 15 moles could be spread across like the entire universe, right? So it could be very dense or very less dense. We don't know that yet. We'll learn about concentration later, but moles strictly indicates the number of particles that we have of that substance. And the mole was like it basically, a singular mole is the number of particles in 12 grams of carbon-12, which is used to define the mole, and everything is measured relative to this. And so that's how the concept of the mole was born. So, yep, now we've gone through the definition of a mole, what it means. So now let's go through Avogadro's constant. So Avogadro's constant is this number that you see here, 6.022 times 10 to the power of 23. That is Avogadro's constant. So let's go through the equations that we'll be using. So the main equation that you'll be using are N, simple N, which is equal to moles, is equal to capital N. So the number of particles divided by N subscript A. So NA is Avogadro's constant. What is Avogadro's constant? 6.022 times 10 to the power of 23. If you guys pull up your chemistry data sheet, Avogadro's constant should be present in your chemistry data sheet. But yeah, so this is one equation, right? So if if a question asks you to calculate how many particles are in 1.5 moles of sodium, what I would do is N is equal to 1.5. And we're trying to find this N, right? We have Na because it's a given value. It's a constant. We know what simple N is. We know the moles is 1.25. We're trying to find N. So what is the number of moles in what is the number of particles in 1.25 moles of sodium? What I would do is I do 1.25 times Avogadro's constant to get a value of 7.5275 times 10 to the power of 23 particles of sodium. So that's how many particles are in 1.25 moles of sodium. So that's that. That's one calculation to find the moles. The second calculation is if they give us a gram value. So if they give us like for example the amount of grams of zinc, right? So say they have a certain amount of grams of zinc, right? So they say we have 8 grams of zinc. How many moles are in 8 grams of zinc? So if I have a weighted mass of zinc as 8 grams, how many moles are in 8 grams of zinc? Well, we look to the formula that has mass in it because they've given us mass, grams, 8 grams, right? So the formula that we use now is N is equal to M over MM, or mass over molar mass. So some schools you might learn these two M's as a simple singular M. So you might run M over M instead of M over MM. I lent it as m over mm because a singular m can be confused for another unit of measurement called molarity, which we'll learn a little bit later. This double m helps us to identify that it's molar mass, not molarity. So yeah, moles is equal to mass over molar mass. So if we're trying to now find the amount of moles of zinc in 8 grams, so how many particles, so yeah, the amount of moles of zinc in 8 grams will do mass over molar mass. So we have mass, which is 8 grams. So we do 8 divided by the molar mass, which is 65.38. To give us a value of 0.12236 dot 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 dot, that's how many moles of zinc we have in 8 grams. Now, if the question asks us to find the number of particles of zinc in 8 grams, what we do is we find the number of moles and then we multiply it by Avogadro's constant. So the number of moles that we have is mass over molar mass, 8 over 65.38, 0.122 moles. We multiply that by Avogadro's constant. After multiplying it by Avogadro's constant, we get a value of 7.36 something times 10 to the power of 22. So still, even though it's 0.122 moles, we still have like a huge number of particles of zinc within that 8 grams. So that's how you would tackle basic basic questions relating to the mole. So now let's go through the relationship between, a quick summary, the relationship between moles mass and Avogadro's number is defined by this equation. So yeah, if I mention now how to find the moles of 1.5, so how many particles are in 1.5 moles of sodium, I would say 1.5 times 6.022 times 10 to the power of negative 10 to the power of 23 to get 9.033 times 10 to the power of 23 particles within 1.5 moles of any substance. So let's go through this one. So a sample contains 1.25 moles of nitrogen dioxide or NO2. How many molecules are in the sample? Well, let's go through this question. What equation do we use? We know one that relates mass and molar mass, and we know one that relates particles and Avogadro's constant. So what is the question asking us? It's asking us how many molecules are in the sample. So we need to refer back to now the equation that links particles and Avogadro's constant. So let's go through that now. Particles and Avogadro's constant. So we go to this equation, n is equal to number of particles divided by Avogadro's constant. It's asking us for, they've given us this amount, the amount of substances in moles. We know Avogadro's constant. We're looking for the number of particles. So we'll rearrange this equation to make this the subject. So we will multiply the amount of moles by Avogadro's constant. So we'll do 1.25 times 6.022 times 10 to the power of 23 to get an answer of 7.52 times 10 to the power of 23 molecules. So why isn't it 7.5275? Well, we look at the lowest amount of significant figures, which in the question that they've given us is going to be 1.25 moles of NO2. So 3 significant figures. We give our answer to 3 significant figures as well. So it should be actually 7.53 instead of 7.52 because it's 7.5275. But yeah, that's how we do that. So what is the sentence in red now? Why do I say, what is it, 3 dots? These 3 dots are therefore. It's like it's a simplification for therefore. So I have this additional sentence saying, therefore, there are 7.52 times 10 to the power of 23 molecules in 1.25 moles of NO2. Well, some of you guys might be wondering, why do I have this extra sentence if I already have the answer written down here? Well, this is a good practice to get into because in the future, when you do a mass, so in the future, especially in HSC chemistry, you might have to do like a full page of calculations for a process called titration, which we'll learn in the future. For those calculation questions, you'll do like a full page of calculations to get a bunch of different answers that you have to combine together to get your final answer. Your final answer won't always your marker. So a marker won't always realize that your final answer is what they're looking for, right? So to signpost to the marker that you've actually answered the question, you'll be like, so I've got an answer of 7.52 times 10 to the power of 23. What does that mean though? Well, to signpost that our calculations have allowed us to achieve the answer, we write this final sentence by saying, therefore, there are 7.52 times 10 to the power of 23 molecules in 1.25 moles of nitrogen dioxide. So this now signposts and directly shows the marker that we've answered the question very explicitly. So that's how you would gain all the marks. So obviously this sentence isn't allocated and a whole mark in our answers. It's just in the marking criteria. It's just making our answers overall more succinct and more clear and easier to understand. So I would recommend, if you have time, writing this sentence for all your calculation questions. So Now let's look at the relationship between moles, mass, and molar mass, which is defined by this equation. Moles is equal to mass over molar mass, where n is equal to the amount of substance in moles, mass is in grams, and molar mass is in grams per mole. So molar mass is the mass of 1 mole of an element. So 1 mole of an element, so when we went to zinc, right? We did zinc is equal to 65.38, that's the molar mass. That means 1 mole of zinc will weigh 65.38 grams. So that's kind of what molar mass is indicating. And the molar mass of a compound, it is the sum. So if we're looking at a compound, right? So if we're trying to find the molar mass of NO2, it is the sum of molar masses of all the elements in the compound. So if we're trying to find the molar mass of NO2, we do the molar mass of N, which is 14.01, plus the molar mass of O2, which is 2 times 16, so 32. That is equal to 46.01. So what is the molar mass of NO2? It is 46.01. So now, if we're trying to find how many grams, like how much does 1.25 moles of NO2 weigh? So how much does this weigh? How much does 1.25 moles of NO2 weigh? Well, we'll go to this equation, right? We're trying to find weight now, so we're trying to find M. So we'll do moles times molar mass, right? So we have molar mass to be 46.01 by adding up the molar masses of N and 2 oxygens. So we have 46.01. They've given us moles 1.25. So if I multiply everything together now, I get 57.5125. That's how many grams 1.25 moles of NO2 would weigh. 1.25 moles of NO2 would weigh 57.5215 grams. So that's how you would manipulate and use this equation. So let's do some more questions with it then. Oh, sorry, no more questions. That was it. So let's go through percentage composition, before we get into the final bit of questions. So what is percentage composition? Percentage composition is used to numerically express the percentage of a component within a substance by mass. So percentage by mass is equal to the mass of the element divided by the mass of the entire compound times 100. And you have to ensure that the units for the numerator and the units for the denominator are the same to get a value as a percentage. Otherwise, you'll have it like a unit value for units over here, so it won't become a full percentage. To get a proper percentage, you need to ensure that the units for the numerator are the same as units for the denominator. So if a question gives you values, make sure that they have the same units so that they're not trying to trick you into finding percentage mass and getting the question wrong. Always ensure the units are the same. So now we can move on to a topic called empirical formula. So let's go through this now. So the empirical formula, what it does is it displays the simplest ratio of the elements within a compound. So empirical formula is essentially what we call the ratio formula. So let's look at this compound, right? C6H12O6. Well, what is the ratios? It's 6 to 12 to 6. What is that? The ratio is 1 to 2 to 1, right? So the ratio is 1 to 2 to 1. So C6H12O6 will become CH20 within its empirical formula, because now it's in a ratio of 1 to 2 to 1 in its simplest form. So its simplest form, empirical formula. Let's look at this one now, S2O2. What is that ratio? It's 2 to 2, so 1 to 1. So the empirical formula will become SO, 1 to 1. So 2 to 2, 1 to 1. So it gets simplified. Let's look at this now. So let's look at this, C6H14. What is the ratio of the elements within the compound? It is 6 to 14. What is that simplified? It's 3 to 7, right? So instead of C6H14, its empirical formula will become C3H7. So that is the empirical formula. And some questions that you might get is they might ask you to find the empirical formula. And this is where we apply the concept that we've learned about moles. Like we put it into application now. So let's calculate the empirical formula of a substance. So let's take a look at this following example. A 100-gram substance contains 38.7% carbon, 9.7% hydrogen, and 51.6% oxygen by weight. Work out the empirical formula. So this means that 38.7, so this substance contains 38.7 grams worth of carbon, 9.7 grams worth of hydrogen, and 51.6 grams worth of oxygen. So that's what this is saying. So now we need to find the empirical formula. So let's go through this now. So we find, first of all, the mass of each substance. So the mass of carbon is, as I said, 0.387 times 100, so 38.7 grams of carbon, 9.7 grams of hydrogen, and 51.6 grams of oxygen. So that's the first step. And if you think back to what I mentioned before now, I mentioned this is where we put what we learned about moles into application. So if you use that as a hint now, you'll realize that this empirical formula, it's referring to, we'll need to use moles to calculate empirical formula. So First, we find the mass. So then if we're trying to now apply our concept of moles and put it into application, obviously now we're going to need to find the moles of these substances. So our next step now is to find the number of moles. So we use the formula mass over molar mass for this, N is equal to M over MM. So let's find the number of moles now. So the moles of carbon is 38.7, which we got from, so the moles of carbon is 38.7, so that's the mass, which we got over here. 38.7 divided by 12.01, so the moles of carbon is 38.7 divided by 12.01, which equals 3.22 moles. Let's go through the moles of hydrogen now. The moles of hydrogen is 9.7 divided by 1.008, which is the molar mass of hydrogen, to get 9.62 moles. The moles of oxygen now is 51.6 divided by 16, which is 3.23 moles now. So can you see now how before we had a ratio of like 440 to like 4 to 1 to 5. So we had a ratio of 415 by mass, like approximately. And now we have a ratio of like 1 to 3, 131 now, or 393. See how the ratio like changes drastically based on the number of moles and the number of mass. So always make sure, a common pitfall for many students is that they accidentally use mass to find empirical formula instead of using moles. So always find the molar ratio for empirical formula, because that changes up the ratio like significantly. So you're working out and your answer will be wrong if you use mass instead of moles. So now that we have this, right? How do we know what the shortest ratio is? Well, we divide by the lowest number that we have. So we have 3.22. Let's divide all these numbers by 3.22 to find our ratio. So the current ratio right now is between carbon, hydrogen, and oxygen is 3.22 to 9.62 to 3.23, right? It's a very odd number. So to find the empirical formula, we divide it by the smallest number from our calculations. What is the smallest number from our calculations? The smallest number from our calculations is 3.22. So let's divide all three numbers by 3.22 now. We get 1 to 2.98 to 1 approximately. So we get a ratio of now 1 to 3 to 1. Let's plug that into our values. Let's plug that into our elements now. So we get 1 carbon, 3 hydrogens, 1 oxygen. So our formula now becomes CH3O. So that's how you find the empirical formula of a object. We use the given values of percentage composition by mass to find the mass of all the constituents. And then we find the moles of all the constituents, and then we find the ratio based on the moles of all these constituents. So that's what we do. Okay, so let's look at another question now. The student knows that a compound contains 32.65% sulfur, 65.3% oxygen, and 2.04% hydrogen by mass. What is the empirical formula of this compound? So we know the percentage composition by mass, but they don't give us the full, they don't give us a value. So before the question gave us 100 grams, now they don't give us 100 grams. Well, the reality is it doesn't matter. So let's say we have 100 grams of the substance, right? Because all we're doing is we're trying to find moles. So the molar ratio will stay the same no matter what mass of this object that we have. So we could have 1 gram, we could have 50 grams, we could have 60, 65 grams, we could have 100 grams, doesn't really matter. So we'll say we have 100 grams of the substance and continue forward like that. So assume the total mass of everything is 100 grams, right? And if we assume the total mass of everything is 100 grams, then we'll have 32.65% of it. So 32.65 grams of sulfur, 65.30 grams of oxygen, and 2.040 grams of hydrogen, following their percentage compositions. Now let's go through the steps and by now finding the moles of each thing. So I do 32.65, divide it by its molar mass. The molar mass of sulfur is, let me quickly find it out. The molar mass of sulfur is 32.06. So to find the moles now, I do 32.65 divided by 32.06 to get a value of 1.018040 ... So yeah, approximately this value over here. So that's the number of moles of sulfur that I have. To find the moles of oxygen now, I do mass over molar mass again. So I have 65.3 grams of oxygen. I divide through that by 16 to get a value of 4.08125 moles. That's the moles of oxygen that I have. Let's find the moles of hydrogen. So I have 2.040 moles of hydrogen. That will become, if I divide through it by the molar mass, which is 1.008, I get 2.0238. So this is the moles of hydrogen that I have now. So now I have the approximate molar ratio of everything. So now let's divide through by the smallest value that we get. So I divide through by 1.018085 dot dot dot. So if I divide sulfur by that value, I get 1. If I divide oxygen by its value, I get, give me 1 second, I would get a value of 3.93, which is, approximately 4. And if I divide hydrogen by that value now, I get 2.0238095, etc. divided by 1.018085438. I get 1.877 or 1.987, which is approximately equal to 2. So you don't need to be too specific with, plugging in like 10 digits of numbers and dividing it through. You just need to get an approximate ratio, right? So you can see, you can also already approximate it over here as 1 to 4 to 2. But by showing that you've done the calculations, you get a ratio of 1 to 4 to 2 over here. And now we can plug this into our ratio. So we can now say, therefore, the ratio of sulfur to oxygen to hydrogen is 1 to 4 to 2. So now we can plug this into our equation, or like into our final empirical formula, by saying now the empirical formula is H2SO4, or sulfuric acid. So that's how we would find the empirical formula for this unknown compound in both cases. So two types of questions where they give you the mass and they don't give you the mass. So that's how we would approach it. If they don't give us a mass, we assume that it has a total mass of like 100 grams, for example, to make things easy for us. So that's how we would go about answering questions like these. So now let's move on to limiting reagent questions. So limiting reagent questions will be recurring throughout your entire calculation type thing, like your entire calculation like questions that you'll face through not just this module but all the way up to module 8 in year 12. You'll always be like implicitly and inherently finding out limiting reagents and stuff. So let's think about an equation, right? So I have A plus B goes to C plus D, right? So let's say now I put I put in values of A and B. So I put in certain amounts of A and B, right? They'll react with one another to produce C and D. But let's say that I put in like too little of A, right? So I put in not enough A for everything to react. So not all of this reacts. A runs out sooner than B because I haven't put in enough A. So the reaction will come to an end when A runs out, right? Because then there's no A left to react. So what do I call this? So if I have too little A for everything to react, then A becomes a limiting reagent and B becomes the excess reagent. I can also think about this another way. So instead of me saying I have put in too little A, I can say I put in too much A. So I put in more than enough B that I'm needed, right? So instead of saying I have too little A and A becoming the limiting reagent that way, I can also say that I have put in too much B, so that more than enough B that I need to react with A. So I have excess B after the reaction is finished. So now B becomes the excess reagent, and by definition, the other reactant, which is A, becomes the limiting reagent. So by definition, the limiting reagent is a reaction that is consumed completely and limits the reaction. It is a substance that runs out first. And then with the opposite of the limiting reagent, which is the other reactant, becomes the excess reagent, and it's the reactant that is left over after the reaction comes to completion, or the reaction ends up finishing. So that's the limiting reagent. So let's answer this question, right? When 8 grams of solid zinc and 35 milliliters of hydrochloric acid react, zinc chloride and hydrogen gas is produced. What is the mass of hydrogen gas produced? The density of hydrochloric gas is 1.15 grams per mole. So if we're trying to find the mass of hydrogen gas produced, so this question will obviously have a limiting reagent, so be prepared for that. What's the first step? The first step for any type of calculation questions, which you should now make a habit going forward, is the first step is to always write a balanced chemical equation. So first, let's write a balanced chemical equation. So we have zinc plus HCl goes into zinc chloride plus hydrogen gas. To balance that out, we put a 2 in front of HCl. So now let's count to see if it's balanced. How many zincs are on both sides? 1 zinc, 2, so equal. How many hydrogens are on both sides? 2 hydrogens, equal. How many chlorines are on both sides? 2 HCl, so 2 Cl and Cl2, so 2 Cl, 2 chlorines on both sides, so it's balanced. So balanced chemical equation right there. Now, let's find the limiting reagent. So to find the limiting reagent, we need to find the moles of each substance and see which one runs out first, right? In this question now, we use a molar ratio. So you can see the molar ratio between zinc to, so this is where the coefficients come into play. So let's look at the ratio, the quantitative ratio, the molar ratios now. So what is the ratio between zinc to zinc chloride? So it's 1 to 1, right? So for every zinc that is reacted in this reaction, So for every 1 mole of zinc that is reacted in this reactant or this reaction, so every 1 mole of zinc that is reacted, 1 mole of zinc chloride is produced, because it's in a molar ratio of 1:1. Similarly, for every 1 mole of zinc that is reacted, 1 mole of hydrogen gas is produced, because it's in a ratio of 1:1. Now, similarly, for every 2 moles of hydrochloric gas reacted, 1 mole of zinc chloride is produced. Similarly, for every 2 moles of HCl reacted, 1 mole of H2 gas is produced. Now, if we were to think of for every 1 mole of HCl reacted, so if for every 2 moles of HCl, 1 mole of zinc chloride is produced, then for every 1 mole of HCl, half a mole of zinc chloride is produced. So that's how we use that formula. That quantitative ratio formula. Similarly, if we're now trying to find the ratio of reactants, if I'm trying to react 1 mole of zinc, I need to put in 2 moles of HCl. If I put in 1 mole of HCl and 1 mole of zinc, what is the limiting reagent? The limiting reagent is going to be HCl, because we need 2 moles of HCl, but I've only put in 1. So I put in less than the amount that I need to have a complete reaction. And so HCl becomes the limiting reagent and zinc chloride becomes the excess reagent, because if I have 1 mole of HCl, then I only need half a mole of zinc to react everything completely, right? Because it's in a ratio of 2:1. So that's how that concept of quantitative ratios or molar ratios would work. All right, so let's go through the next part now. So we have the balanced chemical equation. Now we find the we find the mass of HCl, right? Because we need to find the moles of both subjects. So we'd find the mass of HCl. How do we do that? They've given us milliliters. They've also given us density. So we just need to multiply these two together to cancel out the units to get grams. So for the mass of HCl, we do 35 times 1.15 to get 40.25 grams. So now we know the grams of HCl. So now we can calculate the moles of HCl as well now. So the moles of zinc is 8 divided by 65.38, which equals 0.122 moles. Similarly, now the moles of HCl becomes mass over a molar mass, which is 40.25 from this value over here, divided by 1.008 plus 35.45. So, HCl, I have to add the molar mass of hydrogen and chlorine. So this is hydrogen, this is chlorine, to get a value of 1.104 moles. Wait, actually it should be 40.25 1.104 moles. So if this is the case now, what is the limiting reagent? Well, let's look back at the molar ratio, right? So if for every 1 mole of zinc produced, 2 moles of HCl is needed, then for every 0.122 moles of zinc used or zinc reacted, we need 0.244 moles of HCl to react it completely, right? Because it's in a ratio of 1:2. So all I have to do to find the number of HCl required is I multiply 0.122 by 2 to get 0.244. So to react all of the zinc, all I need is 0.244 moles. How many moles do I have though? I have 1.104 moles, right? So I have an excess by around 0.9, right? So I have an excess of like around 0.9 moles. So what is my excess? What is my limiting reagent? Well, zinc is my limiting reagent because zinc runs out first, and HCl will have an excess. We have too much HCl, so HCl will become an excess. So there'll still be HCl remaining after the reaction comes to an end. So that's the limiting. This is the limiting. This is the excess. So we use the limiting now to calculate our molar ratios, because with excess, if we use our excess, then we need to calculate the remaining, and then we use the remaining as a molar ratio. It's too much hassle and it takes a lot of time. So we just use our limiting reagent to calculate the amount of moles reacted. So to find the limiting reagent, we use molar ratio. So the molar ratio of zinc to HCl, to explain it in better detail now, the molar ratio of zinc to HCl is 1.2. So therefore, 1 mole of zinc is equal to, if 1 mole of zinc is approximately now 0.122 moles, then 1 mole of zinc needed for 1.01, so 1 mole of zinc needed for 1.104 moles of HCl is 0.552 moles. So we only have 0.122 moles instead of 0.552 moles. So we have less zinc than we need. So zinc now becomes the limiting reagent. So that's the other way of thinking about it. I can think about it from the zinc's perspective by saying for zinc, we need 0.244 moles of HCl. So we have excess of HCl. So therefore, by definition, zinc is the limiting reagent. But you can also think about it from the hydrochloric acid's perspective. So it's in a ratio of 1:2. So for every 2 moles of HCl, I need 1 mole of zinc. So for every 1 mole of hydrochloric acid, I need half a mole of zinc. So for every 1.10 mole of HCl, I need 0.552 moles of zinc. How many do I have? I have less than that. I have 1.0 0.122. So I have less zinc than needed to react with all of the HCl, and therefore zinc becomes the limiting reagent. So that's how that mentality works. So I can think about it from the zinc's perspective or the hydrochloric acid's perspective. Either way, I get the same answer. Or I come to the same conclusion. So that's how that works. So now we have the limiting reagent now. So we haven't answered the question yet. We still need to find the mass of hydrogen produced. This is the final mark, right? So we know zinc is a limiting reagent, and this is important because we always use the limiting reagent in our calculations. Because as I mentioned before, it's too much of a hassle. So if we're trying to use molar ratio to calculate the amount of moles, so we always use the limiting reagent because that's where the equation, the reaction ends, right? When the limiting reagent is consumed. So how many moles of zinc chloride or how many moles of hydrogen gas will be produced? Well, I mentioned earlier that the molar ratio is 1:1, right? For every 1 mole of zinc produced, 1 mole of H2, so for every 1 mole of zinc consumed, 1 mole of H2 is produced, right? So if zinc is the limiting reagent, which means zinc runs out first, then we've used up 0.122 moles of zinc, right? So then if for every 1 mole of zinc consumed, 1 mole of H2 is produced, then for every 0.122 moles of zinc consumed, 0.122 moles of H2 will be produced. So how much H2 is produced? 0.122 moles, dictated by its 1:1 molar ratio. So therefore, now we have the amount of moles. Let's do mass over molar mass to find the answer to the question, right? So let's use mass over molar mass by saying now, because we're trying to find mass, right? So we'll rearrange this equation. So we'll do 0.122 is equal to mass over molar mass, which is 2 H's. So I do 2 times 1.008. So now I multiply both sides by this denominator to get 0.25 grams as my mass. So we don't need to worry too much about significant figures for this question because we're doing this for our understanding. But this is the general gist of how we'd find the molar ratio or the mass. So we'd find how we'd answer the question using our understanding of limiting reagents. So for limiting reagents, a quick summary now, we've applied our understanding of molar and quantitative ratios, and we've also applied our understanding of limiting reagents and our understanding of the mole concept itself. So that we were now combining all our concepts together to answer calculation questions. And this concept of the limiting reagent will be very prominent in our calculations later, as you can see, because no matter what calculation we do, we need to see at which point the reaction is finished, right? So we need to check if everything reacts to completion or if, at a certain point there is a limiting reagent, and there's an excess reagent as well. So there's always something that we need to know in doing a calculation question. And so you'll come across this concept quite often. Yes.